Welcome back to this module. Now we define bounded and unbounded sets of real numbers. Two concepts are important, bounded above and bounded below. We define both of them one by one as follows. So, the definition goes as follows. Let S be a non-empty subset of R. The set S is said to be bounded above if there exists a number, real number of course, real number say u, such that S is less than equal to u for all S in S. That means, all the elements are bounded by u. Now, each such u is called an upper bound of S, upper bound of S. In a similar manner, the set S is said to be bounded below if there exists a real number say W, such that S is greater than equal to W for all S in S. Each such W is called a lower bound of S. Each such W is called a lower bound of S. Now, the last part of this definition is a set S is called a bounded set, if it is both bounded above and below. If it has an upper bound and if it has a lower bound both, then we say that S is a bounded set. Let us look at few examples. Take for example, the set S 1, 2, 3 up to 100, which is of course a subset of R. The question is whether this set is bounded above or below. Take the element 110, it is a real number. Now, you can see all the members of S, all members of S are less than 110. Similarly, take the element 0 belong to R, then you can see all elements of S are greater than 0. Therefore, there exists at least one element, we can find out at least one real number which is greater than all the elements of S, and we can find out at least one element which is less than all the elements of S. It means the set S is bounded, that is, it is bounded both above and below, and therefore, it is bounded. And from here you can say 110 is an upper bound and 0 is a lower bound of this set S, particularly this particular set. Now, take another example, the set of natural numbers, which is 1, 2, 3 and so on up to infinity. Here any real number less than or equal to 1 is a lower bound. What about an upper bound of this set? Now, suppose if you think that there is an m, a real number such that all the natural numbers are less than this m, what would happen? The question is, can we find such an m? There is a property called Archimedean property, by which we are going to see that such an m cannot exist. Okay? And therefore, this we will prove later, and therefore, this set n, the set of natural numbers, is bounded below, but it is not bounded above. Take another example, the set, the interval 0 1 or the 0 1 open interval, or the interval from minus infinity to 5. From the above discussion, you can at once determine which of these intervals will be bounded and which of them will be not. This is bounded, definitely. This is also bounded, but this is bounded above, not bounded below. Now, do you think that the boundedness of this set and the boundedness of this set are the same, or they are somehow different? You can see here 0 is a lower bound and 1 is upper bound. 1 is also an upper bound. Here also you can see 0 is a lower bound and 1 is an upper bound. What is the difference between this lower bound and this lower bound and this upper bound and this upper bound? You can see this lower bound 0 belongs to this set, this upper bound 1 belongs to this set, but here 0 is not included in this set and 1 is also not included in this set. What does that mean? It means that a set may contain the lower and upper bounds or may not contain upper and lower bounds. The next thing is, in this case, is like how many such upper bounds of a set can exist? How many upper bounds, if it has an upper bound, at least one upper bound, how many upper bounds of a set can exist? How many lower bounds of a set can exist? Of course, under the condition that it has at least one upper bound and it has at least one lower bound. The next question is, of course, can we compare these upper bounds and these lower bounds? The next question will be, can we compare these upper bounds and lower bounds, right? And this leads to the definition of supremum and infimum of a set. We are now going to define formally what is a supremum of a set and what is an infimum of a set. The formal definition goes as follows: let S be a non-empty subset of R. If S is bounded above, then a real number U is said to be the supremum of S, or the least upper bound of S, if it satisfies the following conditions. What are they? The first one is U must be an upper bound of S, and U must be the least among all these upper bounds. How that can be defined? If V is another upper bound of S, then U must be less than equal to V, right. So, the first condition says that all S in S, U must be greater than equal to S. Second condition says that if there exists another V in R such that V is also greater than equal to S, then V must be greater than equal to U also. Then this U is called the least upper bound or the supremum. Right. Similarly, we can talk about the infimum. If S is bounded below, then a real number W is said to be the infimum of S if the following conditions are satisfied. Following conditions are satisfied. The first condition should be W is a lower bound, of S. The second condition is if T is another lower bound of S, then T must be less than equal to W. Then T must be less than equal to W. Okay. So, what does that mean? If W is a lower bound of S, that means for all S in S, W should be less than equal to S, that is condition 1. And condition 2 says that if T is another real number such that T is less than equal to S, then T must be less than equal to W. So, W is the greatest and it is called infimum or the greatest lower bound of S. Greatest lower bound of S. Now, remember that for a non-empty subset in R, to have a supremum, it must have an upper bound. Thus, it is not necessary that every subset of R has a supremum. In the same manner, we can say that not every subset of R has an infimum. Indeed, there are 4 possibilities for a set S to have. They are 4 possibilities. Possibility 1, it has a supremum, but not an infimum. Secondly, it has an infimum, but not a supremum. Thirdly, it has both a supremum and an infimum. And finally, it has neither a supremum nor an infimum. Nor an infimum. Again, note that the number u is a supremum of some set S in R, subset of R, if U is an upper bound and for all upper bounds V of S, we must have U should be less than equal to V. This we can put it in an alternative manner, that any number smaller than U can never be an upper bound of S. So, what we can say, any number smaller than U can never be an upper bound of S. That is, mathematically, if Z is less than U, then Z cannot become an upper bound of S. It means, if it is not an upper bound of S, there exists, that is, there exists at least one S in S such that S is greater than Z. These derivations or these conclusions are very much important for us to have different properties in this particular domain. And does the following statements about the supremum are equivalent? We will use these variants in different problems as per their convenience. The first one is, let U be in R be the supremum of a non-empty set S, which is a subset of R. This is equivalent to, if V is any other upper bound, then U must be less than equal to V. It is also equivalent to, if Z is strictly less than U, then Z cannot be an upper bound of S, which is again equivalent to, for epsilon greater than 0, there exists some S epsilon in the set S such that U minus epsilon, which is smaller than U, this is less than S epsilon. That is, what it means, U minus epsilon is smaller than U. This is actually our Z in this statement. Then Z cannot be an upper bound, that means U minus epsilon cannot be an upper bound, but it eventually means that there exists something, some S epsilon in S, because it is not an upper bound, at least one element from S will be there, that will be greater than U minus epsilon. S will be greater than U minus epsilon. So, these four statements are, they are equivalent. They are all equivalent. In what follows next, we try to explain once again with an example of these statements, as this idea is very crucial. Take for example, the set 0 infinity. This is bounded below. So, if you want to find the lower bounds, they make the set of elements which are less than equal to 0. So, the lower bound set of lower bounds will be anything x which is less than equal to 0. X is a real number. Any real number which is less than equal to 0 will be a lower bound of this set. 0 is also a lower bound, also a lower bound, right. Take any real number, take any real number greater than 0. Say let us take 0.001, it is a real number. Now, the question is, can this 0.001 is be a lower bound of 0 infinity? Can 0.001 be a lower bound of 0 infinity? The answer is no. Why? Since you can always find another number, say 0.0001, which is smaller than 0.001, and this 0.0001 is also in this interval, right. Therefore, this 0.001 can never be a lower bound of 0 infinity. Thus, you must have a feeling that 0 is the infimum of this set, but to prove this formally, we need some further mathematical arguments. This we will show in the following sessions.